Yeah, thanks a lot. And thanks a lot that I can present my quite new CD lab. As Professor Bischoff also mentioned that it was the opening ceremony was last week. It's difficult for me now after Professor Bernkopf to show something new because I think we have a lot of things that we do in the same things. Just want to mention my consortium. So it's Andritz, Hydrotech, then Rotax BRP with small engines, Everlands, which was former MAN Energy Solutions with the large engines, Palfinger and Magna Powertrain with the center in St. Valentin. So I think you all know this figure. We in our CD lab or in the field of physics-driven machine learning, we usually talk about, okay, if we have a lot of physics or if we have a lot of big data, in the right path, this is the conventional machine learning. I always say it's the Google approach where we have a lot of data, but we have the disadvantage that it's a kind of black box models, but we have real big data. Usually in our cases, so in mechanical engineering, we usually don't have that much data. We have really small data. But what we have a lot of physics. So mechanical engineering, we have formulas and the physics behind it for more than 100 years. And from our point of view, we should not forget about that because we know how it should work and we know the physics and we want to combine this with traditional machine learning models. And as Robert also said, I come from the large engine field. So my research also is related to turbulent combustion. And turbulent combustion simulation is not that easy. Oh, it's passt schon. So that was a trap for you. Combustion modeling, turbulent combustion modeling. You can see here a small animation. This is a numerical simulation of a diesel flame, and for this kind of simulations, there are you have to consider something, and there are different models available for this. And one model is called the flamelet model, which is related to that this turbulent flame is visualized as an example of small laminar flames, which can be described more easily. And it can be described in this kind of stagnation plane. You don't have to know these facts, but this small flame then can be described with this partial differential equation. It's a diffusion reaction equation. So where you have this is the mass fractions of all the species that are involved in the chemical or in the combustion. You have some combustion parameters, and on the right hand side, and this is the real tricky one, this is then the reaction term. This is how the chemistry comes into play, and that's the challenging task if you want to simulate combustion. It's always the chemistry because that's the most complex thing. And in typical numerical simulation in CFD, the workflow is like that. You solve this partial differential equation for a huge parameter space. So you have several features, you have a lot of data, and you put this data into tables. And what you then use in your CFD simulation is use this data as a lookup table. And in each time of your simulation, you go into the table, look, okay, where is my flame, or how is the property of my flame, and put it back to your numerical simulation, and then you go further in time, and you then describe your flame. And there are three things to consider here that can be some kind of bottlenecks. Is on the right hand side, there's a high computational demand because you have to always make for each cell, and you probably have 2 million cells. You always have to make a numerical interpolation in a higher space. And also the generation of the data is highly computationally expensive. And what we use for that to come over these drawbacks is we use physics-informed neural networks, and I think you all know the concept. Also, Professor Bernkopf mentioned it, where we plug in the differential equation into the loss function of our neural network. And this looks like that. So we have our partial differential equation, we have our neural network, and we have additional residuals of our partial differential equation for each species that has to be solved. And the problem is the chemistry there, because usually it is done by a chemistry solver, which is an external solver. But the chemistry solver has to be plugged into the neural network. So we had to write a differentiable chemical solver that is able to be plugged into the numerical to the pin. We tried this out and we solved this. I show it now for a small application. It's a one-step hydrogen combustion, and you can see here for each species, where we have 4 species, we have on the left-hand side the numerical simulation, which evolves in time. The right-hand side, we have the pin, which gives us, as you see, the same results. Here, the scatter plots, which you can see we get the correct solution. But what is always the problem is that all people say, okay, but you have the training time of your neural networks. And of course, this is right. The neural network takes more time to train if the feature space is small. So if you have a small space of features that should be covered by the data, for example, if you only have 2 features, the numerical simulation is much faster than the pin. But if we increase the number of features, for example, from 2 to 3, the pin gets better. And we think, and we believe that if we increase the features more to 4 and 5, it's getting even better. And with that, we would have a new combustion model, because the combustion model now, this one, is only valid for very small feature space. For example, it can only be used for isobar combustion. It can't be used in an internal combustion engine because the flame is not isobar. But with that approach, with using pins for that, we are able to use this also for internal combustion engines. We would have a new combustion models created by physics-informed neural networks. So just one teaser for my CD lab, and thank you very much. And I'm open for discussions in the lunchtime. Thanks.
Any questions? Oh, you're closer.
So you mentioned that, for example, for that model that you were showing with the flame, like you're having a subset, like coverage of the problem by the solver, right? So how do you make sure that what the ML model is doing is not like a low-rank compression of the hash table that you were mentioning, and it works outside of the domain? No,
because we have the physics behind it. And we have in all the collocation points that we use for training, the physics has to be resolved. So if we can, it's not only an interpolation, it's a physics aware interpolation. And we did some tests and we saw that it's the table. It's even more accurate than using the table, just in the simulation, because when we use the table, we have a linear interpolation between the data, and we have the pin, we have the physics correct interpolation from the neural network. Physics more correct interpolation.
More questions? Maybe. Yeah. So.
Let's go for lunch.
Okay. So let's. Okay. Yeah. Good. So we actually. So yeah. So okay. We're anyway over time. So let's go for lunch. And,